In 2019, every solar physicist on Earth agreed the next 11 years would be calm. Solar cycle 25 would be the quietest in decades. A gentle hum from our star. Nothing to worry about. They published the forecast. They staked their reputations on it. And then, sometime around late 2024, the data started coming back wrong. Not slightly off, catastrophically wrong. The sun wasn't winding down, it was winding up. Sunspot counts exploded past predictions. Magnetic poles began drifting out of sync. And deep inside NASA, someone realized we'd been building our entire technological civilization on a promise the sun never actually made. Stay with me, because what they found isn't just surprising. It rewrites everything. Stay with me, because our star's true nature is still unfolding as real-time measurements pour in from the solar frontier. Researchers are watching whether these magnetic disruptions will break every forecast we've relied on, or validate the unsettling theories about Terminator dynamics. Subscribe so you don't miss what happens next, because the data arriving could fundamentally reshape how we predict and prepare for what the sun does next. Now, let's settle in and unravel this together. In 2019, the world's top solar scientists gathered their data, ran their models, and made a promise. They told us solar cycle 25 would be quiet, unremarkable, a sleepy chapter in our star's 11-year rhythm. Peak sunspot numbers around 115 by mid-2025. Minimal geomagnetic storms. Low risk to satellites. The kind of solar cycle where you could set your watch by it and go back to worrying about everything else. NASA published the forecast. NOAA's Space Weather Prediction Center backed it up. The scientific consensus was clear. We were entering a lull. But here's the thing about promises made to a star that's been burning for 4.5 billion years. It doesn't care about your models. It doesn't care about your consensus. And it certainly doesn't care about your satellites. Because as we sit here now in late 2025, something has gone catastrophically wrong with that prediction. Not just a little off, not within the margin of error, completely, fundamentally wrong. The sun isn't behaving like the quiet, predictable furnace we were promised. Instead, sunspot counts have been spiking well above forecasted ranges. Activity levels that weren't supposed to arrive for months showed up early and stayed late. The smooth bell curve scientists expected has turned into a jagged staircase of surges, each one climbing higher than the model said was likely. Solar maximum, that peak period of activity, didn't wait for our schedules. It arrived ahead of time and brought friends we didn't invite. NASA confirmed it in late 2024. We are officially in solar maximum now, and the activity isn't winding down the way it should. It's sustaining, persisting, acting. Like the sun read the forecast and decided to do the exact opposite just to make a point. Now, you might think this is just scientists being overly cautious about getting a prediction slightly wrong. Weather forecasters miss rain predictions all the time, right? But this isn't about a missed decimal point. This is about the entire framework being insufficient. Solar cycle forecasting has actually gotten quite sophisticated over the decades. Scientists track magnetic fields deep inside the sun. They measure plasma flows. They build elaborate models that simulate the churning interior of our star. These aren't wild guesses. These are computational models built on decades of observation and physics. And yet, they miss this. All of them. The reason that matters, the reason this isn't just an academic embarrassment, comes down to what a quiet sun was supposed to give us. Safety, predictability, a reprieve. Our modern civilization runs on infrastructure that is shockingly vulnerable to solar outbursts. Satellites that handle GPS navigation, weather monitoring, communications, military operations, power grids with transformers that can be fried by geomagnetic currents. radio systems that black out during solar flares, astronauts on the International Space Station who need advance warning before radiation storms hit, airlines that reroute polar flights when space weather gets rough. A quiet solar cycle meant all of that could breathe easier. Mission planners could schedule satellite launches without excessive concern. Grid operators could defer expensive hardening projects. We could keep filling low Earth orbit with thousands of new satellites without worrying too much about atmospheric expansion, making them fall back to Earth prematurely. That promise of calm has evaporated. Instead, we're seeing X-class flares, the most powerful category, with uncomfortable frequency. Coronal mass ejections hurling billions of tons of magnetized plasma toward Earth. Geomagnetic storms triggering aurora displays at latitudes where they're rarely seen. All of this happening during what was supposed to be a weak cycle. But here's where it gets truly unsettling. It's not just that the sun is more active than predicted. It's that the activity itself looks wrong. The pattern doesn't fit. When you plot sunspot numbers over time, you expect a relatively smooth rise to peak, then a gradual decline. A bell curve. Maybe a bit lumpy, sure, but recognizable. What we're seeing instead resembles something far more chaotic. Sudden jumps, plateaus where there should be slopes, values that spike and refuse to come back down. Scientists have a term for when systems don't behave according to their models. They call it emergent behavior. Complexity that arises from interactions the model doesn't capture. And our sun, it turns out, has complexity we never fully appreciated, particularly in the magnetic processes happening deep below the visible surface. The photosphere we see is just the skin. Underneath, there's a roiling interior where magnetic fields are generated, twisted, amplified, and destroyed in ways we're only beginning to understand. This brings us to a term you're going to hear more about. A term that sounds like it belongs in a science fiction movie, but is actually rigorous solar physics. The Terminator. Not a robot from the future, not a metaphor. An actual event in the sun's magnetic cycle where old magnetic bands from the previous solar cycle finally cancel out and new bands take over completely. Scientists thought this was just a handoff, a smooth transition, one magnetic generation retiring while the next clocks in for its shift. Except it's not smooth at all. It's a trigger event, a point where the magnetic architecture of the entire sun can reorganize abruptly. And when that happens, all bets are off. The models that assume gradual, predictable change suddenly have nothing useful to say, because emergence doesn't care about your assumptions. Why are scientists uneasy about this? Because Terminator dynamics imply something most solar models don't account for: discontinuity. The idea that the sun doesn't just oscillate in a predictable rhythm, but can shift suddenly from one state to another. That underneath the seemingly regular 11-year heartbeat, there might be switches and thresholds, tipping points where small changes cascade into large effects. And if that's true, if the sun operates not like a metronome, but like a system balanced on the edge of stability, then everything we've built assuming predictability is suddenly on much shakier ground than we thought. But the surface activity, as dramatic as it is only the beginning. Because what we're seeing in sunspot counts and flare frequency is just the symptom. The real story, the truly strange story, is happening at the sun's poles, where the magnetic field itself is coming apart in ways we've never directly observed before. And that's where things stop being merely surprising and start becoming genuinely alarming. Let's talk about how the sun is supposed to work. Every 11 years, give or take, the sun's magnetic field does something extraordinary. It flips. North becomes south. South becomes north. The entire global magnetic structure reverses polarity. This isn't a metaphor or an approximation. The sun's magnetic poles literally swap places. And this flip is what drives the solar cycle. When the field is organized and strong, you get lots of sunspots and activity. When it's transitioning and weak, things calm down. Then the flip completes. The field reorganizes in the opposite direction, and the cycle starts again. 11 years up, 11 years down. 22 years for a complete magnetic round trip. This has been the framework for understanding solar activity for decades. A relatively simple, elegant model. The sun is basically a giant dynamo, generating magnetic fields through the rotation of its electrically conducting plasma. The fields emerge, they twist, they flip, they settle, rinse and repeat for billions of years. Except we never actually saw the poles directly. Not really. The sun's rotational axis is tilted only about 7 degrees relative to Earth's orbital plane, which means we mostly see the sun's equatorial regions. The poles are foreshortened, hard to observe clearly. Scientists had to infer what was happening at high latitudes through indirect measurements, magnetic field models, computer simulations, educated guesses based on lower latitude observations. Until now. Because in 2020, the European Space Agency launched Solar Orbiter, a spacecraft specifically designed to get out of the ecliptic plane and look down on the sun's poles for the first time. And in 2024 and 2025, as it reached the right position, it started sending back images and data that made solar physicists very uncomfortable. The poles don't look like poles, not the way we imagine them. Instead of nice, organized regions with clear north and south magnetic orientations, Solar Orbiter revealed a patchwork, a chaotic mess of mixed polarity regions. Little magnetic islands with north and south orientations jumbled together like a shattered mirror, the kind of structure that doesn't fit neatly into simple dipole models. This is a problem, because if the poles are fragmented, if they're not acting as coherent magnetic regions, then the global field structure becomes much more complicated. The sun isn't just a bar magnet that flips. It's more like a collection of smaller magnets, all jostling for dominance. And the overall field is whatever emerges from that chaos. But it gets worse. Data suggests the north and south poles aren't flipping in sync. The northern magnetic pole appears to be ahead in its transition. The southern pole is lagging behind. They're out of phase, desynchronized. And that creates a situation solar physicists have speculated about, but never directly observed: a quadrupole field. Instead of one north-south magnetic axis, you effectively have two, overlapping and interfering with each other. Why does this matter? Because magnetic fields are what contain the sun's plasma. The charged particles that make up the sun are trapped and guided by magnetic field lines. When the field is coherent, strong, and well organized, it does a good job of holding everything in place. But when the field becomes complex, when it develops multiple poles and strange geometries, containment weakens. Plasma that should stay put finds ways to escape. Energy that should dissipate gradually instead builds up and releases violently. Think of it like trying to hold water in your hands. If you cup them together properly, you can hold quite a bit. But if your fingers are misaligned, if there are gaps and irregularities, the water finds every weak point and spills through. The sun's plasma is doing the same thing. Wherever the magnetic field has inconsistencies, plasma erupts, outward, flares, coronal mass ejections, jets and filaments. And there's another factor making this worse. The sun doesn't rotate as a solid body. The equator spins faster than the poles. This differential rotation twists magnetic field lines like rubber bands being wound tighter and tighter. Over time, this stores enormous amounts of magnetic energy. Eventually, something has to give. Field lines break and reconnect in explosive events. But when the poles are out of sync, when the global field is already disorganized, those reconnection events can be much more violent and unpredictable. Scientists call this magnetic shear. It's the mechanism behind solar flares and CMEs. The more twisted and stressed the field lines get, the more energy is available for explosive release. And right now, with desynchronized poles and a fragmenting magnetic structure, the sun is storing energy in configurations that our models didn't anticipate. Previous solar cycles didn't have this problem. Or rather, we don't know if they did, because we couldn't see the poles clearly enough. Solar Orbiter is giving us the first high-resolution view of polar regions during a magnetic reversal, and what we're seeing doesn't match the textbook description. The poles we imagined were orderly. The poles we're actually observing are chaotic. This has implications for every subsequent phase of the solar cycle. If the magnetic field isn't reorganizing the way it's supposed to, if it's creating complicated multipole structures instead of simple dipoles, then the behavior of the next cycle becomes much harder to predict. The baseline assumptions break down. Models that worked reasonably well for past cycles might be useless for future ones. And here's the existential question nobody wants to say out loud. What if this isn't an anomaly? What if the quiet, well-behaved solar cycles of the past few decades were the anomaly? What if the sun's natural state is this, chaotic and unpredictable, and we just happen to build our entire technological civilization during a brief period of unusual calm? We don't know. We can't know, not yet. But the data we're getting from Solar Orbiter suggests that the sun is far more complex than we gave it credit for. And complexity in dynamical systems is another word for unpredictable. So the poles are out of sync. The magnetic field is fragmenting. Energy is building up in twisted, stressed configurations. But those are still just the conditions, the setup. The real question is, what pushes the system over the edge? What turns magnetic complexity into explosive activity? That's where Terminator dynamics come in, where overlapping magnetic bands collide and create effects nobody modeled. And that's what we need to talk about next. We've been thinking about the solar cycle wrong. For decades, textbooks have described it as an 11-year rhythm. Activity rises, peaks, falls, and bottoms out. Then it starts again. A simple sinusoidal wave, up and down. Peak and trough, as predictable as a metronome, or so we thought. But there's another way to think about solar cycles, one that paints a very different picture. Instead of one cycle ending and another beginning, imagine two magnetic systems overlapping. The old cycle hasn't quite finished its work when the new cycle starts waking up. For a period of time, both exist simultaneously. Old magnetic bands drifting toward the equator from higher latitudes. New bands forming and beginning their own migration. Two generations of magnetic architecture occupying the same star. This isn't speculation. Observations show exactly this pattern. Old cycle magnetic fields persist well into the new cycle. They coexist. They interact. And those interactions are where things get interesting, because magnetic fields don't just sit next to each other politely. They interfere, constructively or destructively, depending on their orientation. When two magnetic bands align, when they point the same direction and reinforce each other, activity amplifies. Stronger fields, more energetic events. But when they have opposite polarity, when they meet head-on, they cancel. The magnetic field strength drops locally. And in that moment of cancellation, something dramatic can happen. Energy that was stored in those fields has to go somewhere. It doesn't just disappear. It converts into other forms. Heat, kinetic energy, explosive release. This is the Terminator event. The moment when the old magnetic bands finally finish their migration to the equator, meet their opposite polarity counterparts, and annihilate. Magnetic north meets magnetic south, and they destroy each other. What's left behind is a clean slate for the new cycle to fully take over. But clean doesn't mean calm. The transition itself can be violent. Here's the critical insight. This isn't a gradual process. It's abrupt. Think of it like two opposing armies that have been marching toward each other. For years, they're far apart. Then they're close. Then suddenly, they're right on top of each other, and everything happens at once. Battle, chaos, reorganization. When magnetic bands collide at the solar equator, the entire magnetic architecture of the sun can shift suddenly. And when that happens, surface activity spikes, flares, coronal mass ejections, sunspot eruptions. Some solar physicists have been arguing for years that Terminator events are real, significant triggers for activity. They've looked at historical data and found suggestive patterns. Cycles where activity didn't rise smoothly, but jumped suddenly. Transitions that looked more like step functions than curves. These were often dismissed or smoothed out in analyses because they didn't fit the standard sinusoidal model. But what if those jumps weren't measurement errors? What if they were signatures of band collisions? If that's true, then our forecasting methods have been missing a crucial piece of the puzzle. Most solar cycle predictions use models that assume smooth, continuous change. They take current magnetic field conditions, project them forward using differential equations, and predict future activity. These models can be quite sophisticated. They account for plasma flows, meridional circulation, and magnetic diffusion. But they treat the solar cycle as fundamentally continuous, one state gradually transforming into the next. Terminator dynamics suggests something different: discontinuity, threshold behavior, systems that can sit in a relatively stable configuration for months or years, then suddenly reorganize when the right conditions are met. This is the mathematics of phase transitions. Water sits calmly at 99.9 degrees. Then you add 1/10 of a degree, and suddenly it's boiling. The sun's magnetic field can do the same thing. Build up stress gradually, then release it all at once when magnetic bands collide. And here's where the desynchronized poles we talked about come back into play. When the poles are in phase, when north and south are flipping together in lockstep, the magnetic band structure stays relatively coherent. The old bands decay together. The new bands emerge together. The Terminator event, when it happens, is clean, decisive. But when the poles are out of sync, everything becomes messier. You get partial cancellations, incomplete transitions, magnetic bands that linger longer than they should in some regions while disappearing prematurely in others. This creates multiple opportunities for collision. Instead of one big Terminator event, you might get several smaller ones scattered across different latitudes and longitudes, each one a little explosion of energy, each one adding to the chaos. The result is activity that doesn't follow a smooth curve, but stutters and spikes unpredictably. Is this what we're seeing now? Maybe. The timing is certainly suggestive. We're at the transition between cycle 24 and cycle 25. The old bands should be finishing their journey to the equator right about now. The new bands are already generating sunspots at mid-latitudes. And the activity we're seeing, those unexpected surges that broke the forecasts, they're happening exactly when Terminator dynamics would predict instability. But we need to be careful here. This is still partially speculative territory. Terminator theory has peer-reviewed papers backing it up, but it's not yet mainstream consensus. Some researchers are convinced, others are skeptical. The evidence is suggestive, but not conclusive. Solar physics is hard because we can't run controlled experiments. We can't restart the sun and see what happens under different conditions. We get one star, one cycle at a time, and we have to build our theories from that limited sample. What we can say with confidence is this: the overlapping band model explains phenomena the simple sinusoidal model doesn't. It accounts for sudden activity jumps. It provides a mechanism for why some cycles are stronger, or weaker than average. It connects surface activity to deep internal processes in ways that feel physically plausible. And it matches what we're observing right now, during a cycle that was supposed to be quiet, but refuses to cooperate. So if the sun's magnetic structure is reorganizing abruptly, if energy is being released in sudden bursts rather than steady flows, how does that energy reach us? How does it traverse the 93 million miles between the sun and Earth? That's where things get even stranger. Because NASA's Parker solar probe, diving closer to the sun than any spacecraft in history, has discovered that the solar wind isn't what we thought. It's not a smooth stream. It's full of something called switchbacks, magnetic structures that whip around and send energy at Earth with shocking efficiency, and nobody saw them coming. In 2018, NASA launched the Parker Solar Probe on what can only be described as a suicide mission. Its job is to fly directly into the sun's atmosphere, the corona, and take measurements in an environment where temperatures exceed 1 million degrees. To survive, it carries a heat shield made of carbon composite that can withstand 2,500 degrees Fahrenheit. The spacecraft gets so close that it's effectively skimming the surface of our star, orbiting through plasma that glows white hot. Why do this? Because there are things happening in the solar wind we can't understand from a distance. Questions that have plagued solar physicists for decades. How does the corona get so much hotter than the photosphere beneath it? How does the solar wind accelerate to speeds of over 1 million miles per hour? What mechanisms transport energy and particles from the sun's surface out into space? Parker's solar probe was supposed to answer these questions, and it has. But the answers are stranger than anyone anticipated, because in those first close passes, in 2018 and 2019, the spacecraft detected something nobody predicted: magnetic field reversals. Not just occasional flips, but frequent, dramatic events where the magnetic field suddenly reversed direction for minutes at a time, then flipped back. The magnetometer data looked like a seismograph during an earthquake. Sharp spikes, complete inversions, over and over. Scientists called them switchbacks. The name is almost too casual for what they represent. These are magnetic field lines that have literally bent back on themselves. Instead of flowing smoothly outward from the sun like water from a hose, they fold and twist into S-curves and zigzags. Imagine a rope whipping back and forth in the solar wind, and you're close. These structures carry enormous amounts of energy, and they do it in a way that traditional models never accounted for. Before Parker, solar wind models assumed relative smoothness. Sure, there would be turbulence, variations in speed and density, but the overall structure would be coherent. Magnetic field lines, pointing generally outward from the sun, carried along by plasma flows. What Parker found instead was organized chaos. The solar wind is full of these switchbacks, especially close to the sun where they originate. They're not rare anomalies. They're common, perhaps even dominant in some regions. The question scientists are still debating is, where do they come from? Several mechanisms have been proposed. One idea is magnetic kinks. As field lines emerge from the photosphere and thread through the corona, they can develop kinks and twists, like a garden hose that gets tangled. When plasma flows along these kinked lines, it creates the reversals Parker detects. Another possibility is flux tubes. Bundles of magnetic field lines that get wound up by the sun's differential rotation, then released suddenly. These tubes could carry magnetic structures that naturally include reversals. A third option involves magnetic reconnection right at the boundary between the corona and the solar wind. Field lines break and reconnect in new configurations, and those reconnection events could create switchback structures that then propagate outward. The truth might involve all three mechanisms, or something else entirely that we haven't thought of yet. But what matters for Earth, what matters for space weather, is what these switchbacks do. They transport energy differently than smooth solar wind does. A steady stream of particles and magnetic field is one thing. Our magnetosphere knows how to handle that. It deflects most of it around the Earth, creating the protective bubble we live in. But switchbacks are different. They're sudden, directional. The magnetic field isn't just flowing past us, it's whipping around, changing orientation. When a switchback hits Earth's magnetosphere, the interaction depends critically on the magnetic orientation. If the switchback's field happens to align opposite to Earth's field at the point of contact, reconnection can occur. Earth's magnetic field lines and the solar wind's field lines link up, creating a temporary bridge. And through that bridge, energy pours. Charged particles cascade down toward the poles. Geomagnetic storms light up. Currents flow through the upper atmosphere and couple down to ground level. This is why metrics like solar wind, speed alone, don't tell the whole story. A fast solar wind with a smooth magnetic structure might pass by harmlessly, but a slower wind with sharp switchbacks and the right magnetic orientation can cause significant disturbances. It's not just about how much energy is coming at us. It's about how it's structured and whether it can couple to our planet's magnetic field. Parker Solar Probe has shown that these switchbacks become more frequent and more pronounced the closer you get to the sun. That suggests they originate near the solar surface, possibly in the photosphere or low corona, and if that's true, then they're connected to whatever magnetic processes are happening in those regions. The same twisted, stressed field lines we talked about earlier, the same desynchronized poles and overlapping magnetic bands. Here's the speculative leap, clearly labeled as such. If switchbacks are signatures of magnetic restructuring events, if they're the result of field lines breaking and reconnecting during Terminator dynamics, then an increase in switchback activity could indicate fundamental changes in the sun's magnetic state. Parker is essentially giving us a real-time readout of the sun's magnetic turbulence. And right now, that turbulence is higher than models predicted. Does this mean energy from magnetic band collisions can reach Earth faster than expected? Possibly. Switchbacks could be the mechanism by which sudden releases of magnetic energy at the sun's surface propagate outward as organized, high-energy structures rather than diffusing into the background solar wind. They could be the delivery system for Terminator events. And if that's the case, then space weather forecasting just got much harder. Because predicting when a coronal mass ejection will launch is hard enough. But predicting when that CME will be full of switchbacks, when its magnetic structure will be optimized for coupling with Earth's field, that's an entirely different problem. It adds layers of complexity that current models don't handle. So we've got a sun with desynchronized poles, chaotic magnetic restructuring, overlapping bands colliding at the equator, and now a solar wind full of magnetic whips that can deliver energy to Earth in sharp, unpredictable bursts. And all of this is happening during a cycle that was supposed to be quiet, a cycle our infrastructure was designed to weather easily. Except our infrastructure wasn't designed for this. It was designed for the sun we thought we understood, the sun that no longer exists. Let's talk about what happens when the sun sneezes and Earth catches a cold. Our modern technological civilization is absurdly vulnerable to space weather. Not in some distant theoretical way, in immediate, measurable, economically catastrophic ways. And the vulnerability isn't because we're stupid or negligent. It's because we built everything during a period when the sun was unusually well behaved. We designed our systems for a quiet star. We got comfortable. And now the bill is coming due. Start with satellites. Low Earth orbit, where most operational satellites live, extends from about 100 miles to about 1,200 miles altitude. This is still technically within Earth's atmosphere, just barely. The air is thin enough that it doesn't slow spacecraft down quickly. Under normal conditions, satellites at 400 miles can orbit for years before needing reboost. But solar activity changes the game. When the sun is active, when flares and radiation hit Earth's upper atmosphere, something counterintuitive happens. The atmosphere heats up, and when gases heat up, they expand. The thermosphere, that layer, between about 50 and 600 miles altitude, can double or triple in density during geomagnetic storms. More atmosphere means more drag, and more drag means satellites slow down faster. Their orbits decay. They need more frequent reboosts to stay aloft. For satellites with propulsion systems, that's an annoyance and a cost. For satellites without much fuel left, or small CubeSats with no propulsion at all, it's a death sentence. They fall. Uncontrolled re-entries are already happening more frequently than planned. Satellites expected to last 5 years might last 3. Mission planners are scrambling. But it's not just about satellites falling. It's about where they fall. Low Earth orbit is crowded now in ways it wasn't a decade ago. SpaceX alone has launched thousands of Starlink satellites. OneWeb has hundreds more. Amazon is planning thousands. China is launching their own mega constellation. There are now regions of LEO where spacecraft are so dense that collision avoidance maneuvers happen weekly. Every piece of debris, every dead satellite, becomes a bullet traveling at 17,000 miles per hour. A collision creates thousands more bullets. This is the Kessler syndrome scenario, where one collision triggers a cascade, and suddenly entire orbital shells become unusable. Solar activity makes this worse. When drag increases, orbital predictions become less accurate. Satellites don't follow their expected paths as precisely. Collision avoidance depends on knowing where everything is and where it's going. When the atmosphere is puffing up and down unpredictably, because the sun keeps throwing radiation at us, that knowledge degrades. Near misses become collisions. The cascade risk increases. Then there's the power grid. This one keeps infrastructure engineers up at night. When geomagnetic storms hit Earth, they don't just affect space. They induce electrical currents in long conductors on the ground. Power lines, pipelines, railroad tracks, anything that spans hundreds of miles. These geomagnetically induced currents, GICs, flow into transformers at substations. And transformers aren't designed to handle direct current, only alternating current. GICs saturate the transformer core. Windings heat up. Insulation breaks down. In extreme cases, the transformer physically fails, melts. Replacing a large power transformer isn't like swapping a fuse. These are custom-made, multi-ton pieces of equipment. Lead times can be a year or more. There aren't warehouses full of spares. If a major geomagnetic storm takes out even a dozen key transformers across a continental grid, you're looking at months of blackouts for millions of people. And that's not hypothetical. It happened in Quebec in March 1989. A geomagnetic storm knocked out the entire province's power grid in 90 seconds. 6 million people without electricity. They were lucky. The storm wasn't stronger. The damage wasn't permanent. But the 1989 storm was a candle compared to what the sun can produce. The Carrington event of 1859, the largest geomagnetic storm on record, induced currents so strong that telegraph operators got shocked. Wires sparked. Fires started. If something like that hit today, with our interconnected, just-in-time civilization, the economic damage would be measured in trillions. Food distribution fails. Water treatment plants shut down. Hospitals run on generator power until the fuel runs out. Modern life stops. Communication systems aren't immune either. High-frequency radio, the kind used for aviation and maritime communication, depends on the ionosphere to bounce signals over the horizon. Solar flares ionize the atmosphere differently, disrupting or completely blocking those signals. Pilots lose contact with air traffic control. Ships at sea go dark. Even satellite communications can degrade during geomagnetic storms, as charged particles interfere with signal transmission. And GPS, which we've become dependent on for everything from navigation to financial timestamps to agricultural automation, GPS signals are weak. They originate from satellites 20,000 kilometers up and arrive at ground level barely stronger than background noise. Solar activity creates ionospheric disturbances that delay and scatter those signals. Position accuracy degrades from meters to tens of meters. In applications where centimeter precision is needed, like autonomous vehicles or precision agriculture, that's unacceptable. The military knows this. Defense departments around the world have been quietly hardening systems and developing analog backups. Submarines carry paper charts. Fighter jets have inertial navigation. Critical communication systems have shielded hardware. But civilian infrastructure? Most of it was built assuming space weather would stay within historical norms. The problem is, historical norms might not be normal. Because here's the uncomfortable truth. The period from roughly 1960 to 2020, the decades during which we electrified everything and went digital, that period happened to coincide with relatively benign solar activity. Solar cycle 19 in the 50s was huge. Cycle 20 in the 60s and 70s was substantial. But from the 80s onward, cycles 21 through 24 were progressively weaker. The modern maximum, they called it. High activity, yes, but constrained, manageable. Nothing that threatened civilization's scale infrastructure. We built everything during that window. We assumed that was normal. But what if it wasn't? What if the quiet sun of the late 20th century was the anomaly, and we're now returning to the real baseline? What if the sun's default mode is chaotic, unpredictable, prone to extreme events, and we just happen to build a technological civilization during a rare lull? That's the question keeping people up at night. Not just scientists, grid operators, satellite operators, insurance companies. Because if the answer is yes, if the sun we're dealing with now is closer to its long-term average behavior, then we've been living on borrowed time. Every transformer, every satellite, every radio system was designed for a star that no longer exists. And this isn't the only system acting strangely. Because when you zoom out, when you look at other planets, other stars, even Earth's own magnetic field, patterns emerge. Patterns of instability and transition. The sun isn't alone in behaving unexpectedly. It's part of a broader picture that's starting to look less like isolated anomalies and more like a fundamental misunderstanding of how dynamic cosmic systems actually work. Earth has a magnetic field. You probably learned that in school. The spinning molten iron core generates a dipole field that extends tens of thousands of kilometers into space. It protects us from the solar wind. It makes compasses work. It's been there for billions of years, stable and reliable. Except it's not stable. And it's not particularly reliable either. We just pretend it is because the changes happen slowly enough that we can ignore them within a human lifetime. But the field is weakening, measurably. Over the past 2 centuries, Earth's magnetic field strength has declined by about 10%. That might not sound like much, but the trend is accelerating in some regions. There's an area over the South Atlantic between South America and Africa where the field is so weak that satellites passing through experience higher radiation doses. Engineers call it the South Atlantic Anomaly, and it's growing. Spacecraft have to carry extra shielding or power down sensitive instruments when they cross it. More concerning is the possibility that we're headed toward a magnetic pole reversal. Not the gradual drift of magnetic north that navigators have to account for, but a full flip where north becomes south. This has happened hundreds of times in Earth's geological past. The intervals between flips are wildly variable. Sometimes a few 100,000 years, sometimes much longer. We're currently in a relatively long stable period, which statistically means we might be overdue. The last full reversal was about 780,000 years ago. What happens during a reversal? The field doesn't just flip instantly. It weakens significantly, sometimes nearly vanishing, then reorganizes in the opposite polarity. The transition can take thousands of years. During that time, Earth's protection against charged particles degrades. More cosmic rays reach the surface. Radiation levels increase. Mutation rates in organisms might spike. Satellite infrastructure becomes more vulnerable. There's even speculation that past reversals correlate with extinction events, though the evidence is weak and controversial. The point isn't that we're definitely about to experience a reversal. The point is that Earth's magnetic field is dynamic, complex, and capable of dramatic reorganizations on timescales humans find uncomfortable, just like the sun's field, and both are generated by similar processes. Dynamos. Rotating, electrically conducting fluids, generating magnetic fields through induction. The physics is universal. Now extend that thinking to other planets. Jupiter's magnetic field is enormous, 14 times stronger than Earth's at its surface, and it's not stable. Measurements from Juno spacecraft show variations in the field structure over just a few years. Saturn's field is even stranger, almost perfectly aligned with its rotation axis in ways that shouldn't be possible, according to standard dynamo theory. Uranus and Neptune have fields tilted dramatically off their rotation axes and offset from their centers. None of these fit the simple dipole model we use as a teaching tool. What about other stars? For a long time, astronomers assumed sun-like stars would behave like the sun. Regular cycles, predictable activity. But as surveys improved, and we monitored more stars over longer periods, surprises emerged. Some sun-like stars show cycles much stronger than anything we've recorded from our own star. Others show irregular activity with no clear periodicity. Still others seem to shut down entirely, showing almost no magnetic activity despite being similar in mass, age, and composition to the Sun. One famous example is Tau Ceti, a star about 3/4 the mass of the Sun and relatively close at 12 light-years. It was thought to be quiet and stable, a candidate for hosting habitable planets. But detailed observations revealed it's actually quite active, with flare rates that would be problematic for any Earth-like planets nearby. Our Sun, during its modern maximum, was comparatively calm by stellar standards. There's also evidence for long period cycles on top of the short 11-year cycle. The Gleisberg cycle, named after the solar physicist who identified it, seems to modulate solar activity over 80 to 90 years. Then, there's the suggestion of even longer periods. Centuries, millennia. These are harder to detect because we don't have continuous instrumental records going back that far. But we can look at proxies. Radiocarbon in tree rings, beryllium isotopes in ice cores. These are produced by cosmic rays, and cosmic ray flux is modulated by solar activity. High solar activity means strong magnetic fields that deflect cosmic rays, so less radiocarbon gets produced. By measuring carbon-14 and beryllium-10 in dated samples, we can reconstruct solar activity going back thousands of years. And what we find is fascinating. The modern era is not typical. There have been periods like the Maunder minimum from 1645 to 1715, where sunspot activity nearly vanished. Europe froze. The Thames in London regularly froze solid enough to hold frost fairs. Then there was the medieval maximum around the year 1000, when solar activity was elevated and global. Temperatures warm. These grand minima and maxima aren't random. They seem to be part of the sun's long-term behavior. But we don't understand what triggers them or how long they last. Could the sun slip into another grand minimum? Or are we headed toward a grand maximum? We don't know. The forecasting models that struggle with 11-year cycles certainly can't predict century-scale behavior. And if the sun can transition between fundamentally different activity states, if it has modes that persist for decades or centuries, then any assumption about future baseline activity is just a guess. Here's where things get speculative, and we need to label it as such. Some researchers have proposed that external factors might influence stellar and planetary magnetic activity. Not internal dynamics alone, but coupling to external magnetic fields. The galaxy itself has a magnetic field. It's weak, measured in microgauss, but it's vast. As the solar system orbits the galactic center, we move through regions with different field strengths and orientations. Could that affect the sun's internal dynamo? Could it modulate Earth's field? Most physicists are skeptical. The energy scales don't seem to match. Galactic magnetic fields are weak compared to internal dynamo processes. But weak doesn't mean negligible if the coupling mechanism is resonant or accumulative. There are precedent cases in physics where tiny periodic forces build up large effects over time. Think of a child on a swing. Each push is small, but timed correctly, they add up. There's no solid evidence for galactic influence on solar activity, but there's also no solid evidence against it. We simply don't have enough data. We've been observing the sun carefully for a few centuries. The galactic orbit takes 225 million years. We're extrapolating conclusions from an infinitesimal sample. What we can say is this: multiple systems are showing variability and complexity we didn't anticipate. The sun, Earth's magnetic field, other planetary fields, sun-like stars. None are behaving exactly as the simplified models predict. And whenever you see widespread deviation from expectations across multiple independent systems, you have to ask whether the models are missing something fundamental. Not in the details, but in the framework. Maybe magnetic dynamos are inherently more chaotic than we thought. Maybe transitions between states are more common. Maybe stability is rarer than instability. And if that's true, if cosmic systems generally exist in dynamic transitional states rather than static equilibria, then the conceptual foundation of how we think about long-term stability needs to change. This applies to stars, planets, civilizations, ecosystems. The assumption that things will continue roughly as they have been, that the future resembles the past. That's called uniformitarianism in geology. It's been a useful principle for building scientific models. But it's not a law of nature. Nature is under no obligation to be consistent for our convenience. So the sun is chaotic. Earth's field is weakening. Other stars show unpredictable cycles. Planets have bizarre magnetic configurations, and we're all floating through a galaxy we barely understand, on timescales we can't directly observe. That's the cosmic context. And within that context, the real terror isn't a single solar flare or one geomagnetic storm. The real terror is something more subtle and more profound. Let's be clear about what the danger actually is. It's not that the sun is going to explode. It's not that a massive solar flare will sterilize Earth tomorrow. Those scenarios are science fiction. The sun is stable on billion-year timescales. Even the most extreme solar events in recorded history didn't cause mass extinctions. The Carrington event of 1859 happened during a time when humanity had no satellites and barely any long-distance electrical infrastructure, so the damage was limited to burnt-out telegraph equipment and confused compass needles. If it happened today, yes, it would be catastrophic economically and technologically, but biologically, humans would survive. Life would continue. The real danger is uncertainty, unpredictability, the erosion of our ability to forecast what comes next. We've built a civilization that depends on knowing what's going to happen. Weather forecasts for agriculture, tide predictions for shipping, orbital mechanics for satellite operations, economic models that assume resource availability, supply chains optimized for just-in-time delivery. All of it assumes the future is extrapolatable from the past. that patterns repeat, that systems behave consistently. But what if they don't? What if the sun, our primary external energy input and a major driver of space weather, operates not as a clock, but as a chaotic system with thresholds and tipping points? Systems like that can sit in apparent stability for long periods, then transition suddenly to a new state. Think of climate. For thousands of years, Sahara was green, then it wasn't. The transition took maybe a century, maybe less. Now it's desert. Did the people living through that transition understand what was happening? Did they have models that predicted it? No. They experienced it, adapted where they could, migrated when they couldn't, and the region's entire ecological and human landscape transformed. Solar cycles might work the same way. Periods of regular, predictable behavior. Then a transition to something different. A grand minimum. A hyperactive phase. A shift in the magnetic dynamo's operating mode. These aren't necessarily catastrophes. They're changes. But changes in systems that support billions of humans are inherently dangerous. Not because the change itself is lethal, but because our ability to respond depends on anticipation. Farmers plant based on expected climate. Grid operators install capacity based on expected demand. Satellite operators launch constellations based on expected orbital lifetimes. If those expectations break down, the infrastructure doesn't work as designed. And here's the philosophical weight of it. We thought we understood the sun. Not completely, of course. Science never claims complete understanding, but we thought we had the basics down. A nuclear furnace fusing hydrogen into helium, a magnetic dynamo powered by differential rotation, an 11-year activity cycle with some variation but fundamentally periodic, simple enough to teach in high schools, reliable enough to design technology around. That understanding is fracturing, not because we were stupid, but because we were working with incomplete data during an atypical period. The sun we studied for the past 50 years was quieter than normal. The poles we modeled were inferred, not observed. The magnetic dynamics we theorized were simplified because the real complexity wasn't accessible. Now we have spacecraft like Solar Orbiter and Parker Solar Probe sending back data that doesn't fit the textbook narratives. And instead of making the picture clearer, it's making it more complex. Complexity is fine for pure research. Scientists love complexity. It means more to study, more papers to publish, more conferences to attend. But complexity is terrible for applied engineering. You can't build a power grid that's robust to all possible geomagnetic storm configurations. You can't design a satellite constellation that survives every possible space weather scenario. At some point, you have to make assumptions. You have to draw a line and say, we'll design for conditions up to this level, and beyond that, we accept the risk. The question now is, where do we draw that line? If the sun is capable of behavior we haven't seen in the modern instrumental era, behavior that only shows up in paleoclimate records or historical anecdotes, how do we prepare for it? We can't. Not fully. We can harden the most critical systems, build in redundancy, develop backup communication methods, keep paper maps, train people to work without GPS. But we can't make all of modern civilization resilient to a Carrington-scale event, or worse. There's a concept in systems theory called metastability. It describes systems that appear stable, but are actually balanced in a high-energy state. They can persist there for a long time, sometimes indefinitely, but they're vulnerable to perturbations. A small push, and they cascade to a lower energy configuration rapidly. Ice on the verge of melting is metastable. A supersaturated solution is metastable. And possibly, magnetic dynamos in stars and planets are metastable. They operate in particular modes, but those modes aren't deeply stable. They're contingent, dependent on conditions that can shift. If the sun is metastable, if its current operating mode is one of several possible states it can occupy, then the question isn't whether it will transition. It's when, and what the new state looks like. A grand minimum would actually be less dangerous in some ways, because a quiet sun means less space weather. But a hyperactive phase, that would stress every system we've built. We'd adapt eventually. Humans are good at adaptation. But the transition period would be painful, expensive, disruptive. And maybe that's the real reframe we need. Maybe stability itself is the anomaly. Maybe the default state of complex systems, whether they're stars or climates or magnetic fields or ecosystems, is change. Slow change, punctuated by rapid transitions. Long periods of apparent calm, broken by reorganizations. And the lesson for humanity, the species that plans and builds and forecasts, is that our plans need to incorporate not just the expected, but the unexpected. Not just the probable, but the possible. This doesn't mean panic. It doesn't mean despair. It means humility. The humility to acknowledge that a star 93 million miles away, which we've been observing intensely for centuries, can still surprise us. Can still behave in ways that break our models and force us to rethink basic assumptions. And if the sun can do that, what about everything else we think we understand? But there's also something liberating in that realization. Complexity isn't always catastrophic. It's also creative. New behaviors, new patterns, new possibilities. The sun isn't broken. It's not malfunctioning. It's just being a star. A dynamic, evolving, complex star. One that operates according to physics we're still learning. And yes, that makes life harder for engineers and planners and infrastructure operators. But it also makes science more interesting, more alive, more real. We didn't find a bomb. We found a star that's more sophisticated than we gave it credit for. A star with magnetic fields that reorganize suddenly. Poles that desynchronize. Energy transport mechanisms we're only beginning to map. And our job, as a civilization that depends on that star for literally everything, is to keep learning, keep observing, keep building models, knowing they'll be wrong, but hoping they'll be useful. And most importantly, keep adapting. Because the sun hasn't changed. Not really. It's been doing this for 4.5 billion years. We're the ones who are new. We're the ones who built a technological civilization in the blink of a cosmic eye and assumed the conditions during that blink were permanent. They're not. They never were. And maybe it's time we caught up to that reality. Not with fear, but with curiosity, with resilience, with the understanding that living on a dynamic planet orbiting a dynamic star was always going to be complicated. We just forgot for a while. Now we're remembering. And that, more than any solar flare, is what will define how the next century unfolds.